Okay, so now we are broadcasting through YouTube also. This is the problem of being the chairman of your own session. You have to control everything. Okay, so now we have generated the profiles, the geodesics of the different geodesics, the various types of geodesics, the direct image, the lens image, and the photon ring. And now we compute some geodesics of internal region. Okay, only 20, we don't need any. And we put everything together. So these are the internal geodesics, all of them are absorbed. Okay, and now we put all of them together with these commands. And you can see what we get. Okay, so this is why we chose different colors. In green, the direct image, orange, the lens image, red and blue, the photon ring, and then in black, those that are absorbed. Okay, and you can compare this plot with the paper by Wald and Grala, Holz, and Wald. This plot here is basically nothing. Okay, so this code is just post-born simply because I didn't understand this plot. I wanted to be able to reproduce it, and that's how we can do it. Okay, it's very elementary if you know the commands. Okay, and now all of you can do this. Okay, so this is the first part of the talk, and now we know how to compute the distribution of geodesics. Now we need to use them to build the intensity profiles. Okay, and this will be in a different notebook. So let me open the other notebook. So I will stop sharing this screen. Files. Okay, and now I share the other notebook, this one. There we go. Okay, maybe 100 before. No, 2. Yeah. Okay. So this is basically what we want to do. As I say, I have a code that does the compute the geodesics from north and south hemispheres. Okay. This represents, it also includes the accretion disk. The accretion disk here is in black. Okay. And you know that the observer is on the right hand side. Here is, for this code, I think we use the integration from 1000, so it's very far away. This is why these geodesics here look like parallel to the axis, so they come from very far away. Okay. So this is an advanced version of the code. So this is a premium version. It's not in the free version, but it's not really difficult to produce all this. Once you know that the when event command is there, you can do anything. Yeah, and if you have interest in doing plot like this or like this, in which the accretion disk is tilted, so it is not head on with the observer. So you can see that there is a difference in the geodesics, okay, the direct image, the lens image, and the geodesics that are absorbed. The inclination is important, okay. So, but it's very simple to change, to adapt the code to do these kind of things, okay. So now, yes, let me read this because this is important. Because what we want to do, we will consider a light ray that emerges from a circular accretion disk at a location RB. Yes, and propagates outwards, reaching the effector with an impact parameter B. What this means is that we have this accretion disk, okay? Then at some radius, like this one, RB, okay? The light ray emerges and goes This geodesic, for instance, touches here and goes towards the detector. Okay, so this geodesic in particular touches here, and then this is in the green sector, and then propagates forward and doesn't hit the axis again. Okay, but these ones here, they touch the axis twice. One here and somewhere over here. I don't know exactly where. Maybe this one. Yes, maybe this one touches here and here. And note that these two cuts, so there is only one geodesic. So this geodesic is taking intensity from this point, okay, then from this other point, and then reaches our detector. Okay, so we will have intensity coming from two different points on the accretion disk, two different radial distances. And the radial distance is important because the intensity is modulated by the redshift. The gravitational redshift depends on the distance to the object, to the black hole. So the location on the disk where the light, the photon is passing is important. So we will need to collect information for each geodesic about the intersection points. So for a given impact parameter, we may have information about the location of the direct image, where the direct image is generated, where the length image is generated, and if we are looking at photons that are in the photon ring, in the photons near the photon sphere, then we will need also information about each intersection with the disk. Okay, so we need to collect information of those points when the light ray hits the axis. Okay, and the axis, the accretion disk in this representation corresponds to here will be angle pi halves. This one will be in 3 pi halves. Okay, and then we may have others like 5 pi halves, 7 pi halves. Okay, so and all that information can be extracted using the when event command. Okay, when the angle is pi halves, save that value of the radius. Okay, when it is 3 pi halves, save that location for a given impact parameter. And if there are further intersections, save those locations. Okay, and we will need that information later.
The total intensity additive.
Exactly, the total intensity is additive. We are assuming that there is no opacity, blah, blah, blah. So all the simplifications possible is what we are assuming. Yeah. Okay, so and also in physical terms, what we need is that the frequency that is observed here is transparent. The disk is transparent to that frequency, because obviously optically an accretion disk is not transparent. Okay? But the radio waves that we are looking at are quite transparent. Okay, to this plasma. Okay, so they can escape. Okay, so that's the idea. And also, when you consider inclined accretion disks, the locations, the intersection points occur at different angles. So you need to take into account the inclination of the disk. Just only that. So the when event condition is modified by the inclination of the disk. Okay, but this can be done easily. Okay, so let's look how this is implemented. Well, in particular, I used this notebook in one of our papers. I don't remember if it is mentioned here. Yes, in this paper here, there is a link to the paper. You are welcome if you cite it. Thank you. Okay, so we were using a line element like this with this radial function. But now for simplicity, I'm going to put a equal to 0. So we are in Schwarzschild. Okay, the simple Schwarzschild. But you just need to, if you change the value of a to something non-zero, you can get the results of the paper. Okay, everything is written in terms of a. So, but we said now a equal to 0. Even the geodesic equation is written precisely for this model. Okay, so you can see that it is straightforward to adapt it to other codes, to other geometries. So now we integrate from 1000, as I said. So we want something very the detector is very far away. And there are some comments here that you can read when you code. Now we have several flags, conditions, so initial condition 0, things that will change when we proceed with the end result. Okay, and now as an illustration, we are going to consider a single geodesic. Okay, a single geodesic that is very close to the critical impact parameter. Okay, and look at the conditions. Our differential equation is this one. This geo right is the right hand side of the geodesic. Okay, for this particular model with the negative sign, so the geodesic is incoming initially. Okay, the condition on the square root is still here with 10 to minus 15. When we identify the minimum, we do the same as before. Okay, but now we have new when events. Okay, when the angle is pi halves, then we are identifying the direct image. Okay, and you save this value of the radius. Okay, when the angle is 3 pi halves, then this is the lens image, and you save this value of the radius. That will be different. Okay, for a given impact parameter, the geodesic is turning around and it will hit the accretion disk at different radii. This is why we are saving them individually. This is the first intersection, second intersection, third intersection, and here we stop. But maybe we identify, if we are lucky and get a geodesic that is turning like 1,000 times, your code is frozen and you don't get any useful information. Okay, so when you get the third intersection, for us that is enough. Okay, and then we stop the integration. Okay, that's it. But we are now collecting this additional information about the angle. This is the only information that we need to generate the profiles, the intensity profiles. Okay, that's it. Okay. Very good. And everything else is just, we represent this sector of the curve if it has a minimum. Then when it has a minimum, we need to continue the geodesic with the outgoing sector. Okay, this is exactly the same as we did before, simply that adding these conditions on the angles. Okay, and then let me execute this with just one geodesic, and as you can see, the direct image. This is the radius, the impact parameter, and the angle, just to make sure that it works. This looks like pi over 2. Okay, this is pi halves, this is the angle, and this is the location at which the vertical axis is reached. It's here, 4.27. Okay, then it continues and it hits here at radius 3.04, and it continues forward and it is now escaping. You know, it's growing the radius. Okay, it's 3.08. So we have 3 different locations for a single impact parameter. Okay, so what we need to do is simply to collect information about different impact parameters and the points at which that ray is taking intensity. Okay, so impact parameter, we get the radius. With the radius, we will be able to compute the redshift. Okay, and with that redshift, we can determine the intensity observed, depending on the frequency. All this was explained by Diego, that the intensity divided the frequency to the cube is a conserved quantity if some conditions, if wonderful conditions for theoretical physicists are satisfied. Okay? For astrophysicists, that is probably completely useless, but for us, it's fundamental. Okay, so we made a simplification, and then we will be able to determine the intensity on our detector using the intensity that we define on the disk, because we model the disk. So we know that the value of the intensity at each point of the disk, but we need to know at which point exactly we want to measure the intensity. Okay, and that information is given by integrating the equation. This impact parameter is touching the disk at this point, and this point. Okay, and this is what we will collect. And then we will add all the intensities for a given impact path. And this will be the intensity observed in our detector. Okay, so this is for just one geodesic, and now we move to other geodesics. We do the implementation. Yeah, for several geodesics, we take the initial impact parameter as 3 times the critical value. We end at 0, okay? And we are going to compute 200 geodesics. So it's time to check again your Facebook or WhatsApp or whatever. Instagram is also a good option. I think I will upload some photos now of the audience. Time to take the photo of all of you. Okay, smile. Excellent. And now it's time for my selfie also. Perfect. Perfect. You are not in the picture. Okay. Any question or comment? So as you can see, if you work on MATLAB or any other software or are able to program in Python, with what I'm explaining can be implemented easily. Okay, so it's not necessary to use this code. You can do it in any other.
This was for non-rotating.
Yeah, for the non-rotating static spherical symmetrical. You have a question?
If the equation is the same plane of the observer, we can see the spin.
Yes, there are some light rays that are bent.
But
I can't read you, but
in the front, we can see the light.
well, you can see the disk, a light ray that goes in that direction, but then there will be rays that are emitted in some directions, that are deflected, and then go almost parallel and can hit you. Yes. Wherever you are, if there is a black hole, you will, and with an aggression disk, you will see something.
So you can see the front.
From above or from, yes, from this part, this is zero impact parameter. So you will see,
yes.
But then you will have radiation also from other impact parameters. I think that from any impact parameter, but there will be, I mean, if the disk is radiating isotropically in all directions, each point is emitting photons, that at least one of them will get to your vector. Okay, so it's finished. So it's faster than I expected. Okay, so we are just computing 200 geodesics, and we are storing the information of these of these points. You can see here. Let me see. Yes, we are generating lists. List 1 is for the directive match. So, and it saves the impact parameter and the location on the disk. Okay. List 2 saves the information of the impact parameter and the location of the second intersection. And list 3, impact parameter and the location of the third intersection. Okay. So we are feeding these lists of data. Okay. And we have computed 200 geodesics. And now we have all of them here. And now I just want to show you that we computed 200 geodesics and 163 are in the directive match. Okay, 15 are in the lens image, and only 1 is in the photon ring. Okay, so this is not enough. So we need more data. Okay, so this is how we proceed. We first scan roughly the whole range of parameters, and then we focus on the region around the photon ring because we need more geodesics around the critical impact parameter. Okay, so this is the initial list, and now we will compute another 200 geodesics in a region around the critical impact parameter. Okay, so we compute those geodesics, and we will add the new list of points to the previous list. Okay, we will get probably from, yes, we will get information for the direct image. We always have the direct image, okay? But we will also get more data about the lens image and the photon. Okay. So we just wait. Any other question or comment? Adria is not here. This button is his.
Alan, you commented that radio frequencies idea were convenient for the analysis.
Yes.
And
Some frequencies, because some frequencies are absorbed, others are. So this is why the astrophysicists are using these radio telescopes in specific frequencies, because they think that those are optimal.
So what I'm trying to say is that maybe the expertise that people are getting already with HI experiments, let's say, cosmological use of radio telescopes, that expertise would be useful to understand NCTs, how they train the telescopes to see things, etc. And also to target, because for instance, with Meerkat, it's a precursor. You can buy time. You can say, look, I want this object to be studied. So you have telescopes towards what you are interested in. So, yeah, targets that are convenient for comparison.
Okay, so now that we have the other set of geodesics, what we do is to add the two lists of data. Okay, the new one that we have computed, we add it to the one we already computed. So this is why we change the name. We define this new with L is larger. Okay, and we use this command union. Okay. Thank you, Luis Silva, for this, because I think he told us that this is a better way to make it faster. Okay. So, and now we have 362 points representing the direct image, 214 for the lens image, and 76 for the photon ray. So now we have a good amount of points representing each type of contribution. Okay. And then we can plot this list of data, okay, using this command, list plot. So we have discrete points, we need to plot them with this command, Mathematica, and we get this representation. Okay, this is the impact parameter, and this is the radial location, okay, on the disk. So for the direct image, we have this linear relation. For the lens image, we see the region of impact parameters where the direct image lives, okay? It's supported only in this region, and the light ring is almost vertical. It's not strictly vertical. Okay? It's not that we have many points. Okay, so it's very close, but almost vertical. This is why we needed to scan that region with so much detail. Okay, and well, I'm not going to explain what these curves are, but it's just the information that we need to relate the impact parameter with the location on the disk. And this curve, this plot coincides with what Gala, Holtz, and Wald have in the table. Okay, so I use the same colors just for the comparison. Okay, so we are going in the right direction, basically. Okay, and now basically we have all the information that we needed about the geometry. Okay, because we know that for a given impact parameter, that light ray is going to hit in these 3 points at most. It will hit at 1, maybe 2, and maybe 3, at least 1. Okay, and we know exactly for all our geodesics, for 400 geodesics, we know we have all this information. Now what we need to do is to put some intensity profile and propagate that intensity to our detector. Okay, depending where the accretion disk is supported, then we will pick intensity from different regions. Okay, and this is what we are going to show. I'm not going to use the intensity profiles that Diego mentioned today, but because I'm focusing on the intensity profile that we use in the paper here. Okay, so it's I'm not so well connected with the current developments, but are sufficiently good to illustrate the importance of the disk. Okay, so I'm going to define an intensity profile by means of this function. Okay, so I'm using an if function. So if x is bigger than the location of the ISCO, okay, because the location disk is made of massive particles. So massive particles can only have circular stable orbits up to some minimal radius. This radius is the innermost spherical circular orbit, okay, the ISCO. And for Schwarzschild, this is square root of 36, so 6. Okay. So for x bigger than 6, then we represent this. So there is the maximum intensity plotted here. The maximum intensity is at the ISCO, the region closest to the black hole. And then intensity profile decays like this to infinity, and there is no matter inside. So we assume that we have a very clean black hole. It's like a fried egg. Okay, that's the black hole, nothing in between, and then the accretion disk. Okay, very good. So we need to define this function. Okay, we just define this, this. And then we define the redshift function. Okay, the square root, the DG factor is the square root of 1 minus 2x. Oh, well, the square root is this part here is the radius. In Schwarzschild, is 0, so x squared to 1/2 is x. Okay, so we have 1 minus 2x is the function A of the line element. Okay, and the redshift factor is the square root of that quantity. Okay, this is a standard in relativity. Okay, so with this factor, with this redshift factor, we now manipulate the intensity of the direct image, and we construct a table. This table contains here the data that we compile from these lists. You know, list 1, list 2, list 3. It has the impact parameter, impact factor. No, impact factor is for the journalists. Impact parameter, yes, impact parameter and radius. Okay, so list 1 is for the direct image. Okay, list 2 for the lens, and list 3 for the photon. So we need to compute the intensity profiles. So the first component is the impact parameter. For this impact parameter, give me the intensity. So this is the intensity at the radius of where that impact parameter is hitting the disk in the direct image. Okay, multiplied is the original intensity, the intensity of the emission multiplied by the redshift factor. Okay, this is what the intensity over frequency to the cube is equal to constant is useful for. Okay, when you integrate over all frequencies, you get a factor of G4 multiplying the intensity on the disk. So we evaluate the intensity at the location where that light ray is hitting. We correct that intensity with the redshift factor, and this is the intensity that we will detect with this impact parameter. This is the impact parameter. Okay, good. So this is the information that we will have on our detector about the direct image intensity. Okay, good. We do the same thing for the lens image and for the light ray, or the photon. And then, since we have this list have been built combining two sets of geodesics, so they are not sorted. So we need to sort the data in order if we want to plot them. Okay, otherwise the list plot would make crazy things. Okay, and now we plot these sets of data, and this is what we get. Okay, this is the direct image. You see? Compare the direct image with the intensity of the accretion disk. The accretion disk is this one, okay? Our direct image is basically the same. All this is 0, okay? But now we also get an image generated by those photons that come from the back side of the accretion disk, and this is the length image, this orange portion, and the green sector corresponds to the photons that are around the photon. Okay, so we have 3 intensity contributions. Okay, the point is that here they don't have any overlap. For this choice of intensity profile, there is no overlap between these 3 contributions. So basically, what we will see is these 3 peaks, 3 regions with high intensity. This is the highest. This has a smaller support. This is distributed in a broader region. This is in a narrower region, and this is just a point, a bright point. So it will be very difficult to see this thing because the total intensity is the integral over the different contributions. So the main contribution is made by the direct image. Okay, the length gives less contribution, and this is just almost a delta function. So it's giving very little intensity. Okay, so we can also change the colors for those of you if you like it, just to give you the command to represent these things in these colors that is useful. And now what we want is to change from the discrete set of points that we have from the integration of those 400 geodesics. We want to build continuous functions that represent the intensity, because with continuous functions we can add the intensity profiles. With discrete sets of data that do not coincide on the horizontal axis, we cannot add them. Okay, so we need to interpolate. So we build this interpolating function for each set of points. Okay, so we build these interpolation functions, but these interpolation functions are only defined in the region where they have support. We want to extend that definition to all space. Okay, and for this we need to use this command piecewise. So we define the intensity of direct image using piecewise in such a way that the intensity interpolating function of the direct image. This piecewise function is defined in such a way that it is 0 away from the domain where the direct image is defined, and where the direct image is defined, it is the interpolating function of that set. Okay? So, and we do this for the 3 sets. Okay, as I said, it is not obvious why we need to do that, all these things for this profile, because they don't overlap. But when they overlap, we will need to do that. Otherwise, you cannot add the intensities. Okay, so we define this thing. Let me see. This is already the interpolating function defined. Now we define these others, and now we can add the 3 intensity profiles. Okay, we define this total intensity of model 1. Okay, and we compare. We can see that the interpolating functions coincide with the discrete set of points that we saw. But this coincides because I'm using 400 points. If I just put 200, you don't see the light ring. Okay, so before panicking, because you don't get the expected results, try to increase the number of points, and you will see all the physics there. Okay, because you did the right thing, but the representation is not good enough. Okay, very good. Now we can, with these continuous functions, we can integrate to get the relative contribution of each sector, and as I said, the total intensity is the integral over the different pieces. Okay, and then you can see that the direct image represents over unity 95%, basically, of the total intensity. We are just doing the integrals. The direct image, we are integrating it between the region of support of that region. Okay, so the direct image represents 95% of the total luminosity. The lens image, almost 5%, and the light ring, 0.2%. So it is very difficult. It is very difficult to detect the intensity of the photon. Okay, and as Diego advanced this morning, the Event Horizon Telescope can only discern intensities that are within 10% of the maximum intensity. Okay, this is 1 or 2 orders of magnitude away. So you cannot see this in any way. Not even the lens image would be difficult to be detected. So the event horizon is only detecting the direct image. Okay. This is why theorists, we can already do some interesting physics or write some papers discussing what cannot be seen. Okay, the lens image and the light image. Okay. Now I don't know what I'm plotting. Yes, I'm plotting the same thing, but with the continuous functions. Okay. And now we can translate this intensity profile into, since we have spherical symmetry, so we only need to transfer this into a density plot in polar coordinates, just to see that this to represent the black hole from our point of view. And this intensity profile takes this one. Okay, and to see this, you just need to use this command, density plot, in mathematics. So it has this built-in command that you take the intensity profile, the total intensity that we define, okay, in terms of interpolating functions, and then density plot can represent that. Okay, but note that we are using 400 points. It takes 2.5 minutes to produce this image. Okay, 2 minutes and a half. It's 150 seconds. So let me see if you can. Can you see the light ring here?
Yeah.
Because this is the direct image. This is the lens image. And this thing is the photon ring. Okay. So it's the same information that is contained here. The photon ring is basically a point, luminous point, high intensity, but it's just a small support. Okay. The lens image is the red ring that we have here. And all this region that is decaying is evident here in the outwards region. Okay, it is decaying and with a maximum. And then dark region, because we have no intensity here in between. Okay, so it's clear the interpretation now. Very good. Okay, so this is how the Schwarzschild black hole would look like if it had an accretion disk, homogeneous, perfect isotropic, not homogeneous, isotropic accretion disk located from the ISCO outwards with nothing in between. Okay, now what happens if we allow the accretion disk to get within the ISCO and reach the photon sphere, the critical up to r equal to 3. So this is what we are going to see now in the next example. So the second model is simply a different function. We just need to change this function. Okay, and we define it in this way. It's 0 always when x is smaller than the photon sphere. So the photon sphere is 3 for the Schwarzschild black hole. So if x is bigger than 3, we have this function. Otherwise, it is 0. So this means that from x0, from x3, we have no intensity, and starting at 3, we have this function. Okay, which is this intensity profile, maximum there, and then decays. What we do, the same thing as before, compute, define the redshift factor, take your list of points. That this is the same for all the disks. Okay, this is information about the geometry. So all the information about the geometry is contained in the impact parameter radius relation. Where does it hit? Directly match one intersection. Length match two intersections. Okay, so directly match, length match, photon ring. We only need to put the specific intensity profile and the corresponding redshift factor. Okay, but the information about the location of the points, simply we need to see if our intensity profile is picking photons from the geometry. We know all the trajectories of the photons, where they are, and then we put our disk, and then if the region that supports the disk has photons, well, there are photons everywhere. But if there is disk in this region, then there will be intensity transferred to the detector. Okay. So we'll repeat all this again. This doesn't take time, so this is very fast. So I don't need to execute it because it's automatic. But in this case, you can see that with the disk going forward towards the center, it's getting closer to the center up to 3, we now see that the different intensity profiles overlap. Okay, now the directive match is this one, the blue, the orange is the length image, and the green one is the photon ring. So now we have an overlap of the 3 sectors. Since each point here corresponds to a different radius, we cannot add these intensities, okay, with the list of points that we have. This is why we need to construct interpolating functions. So the interpolating function for the directive match, for the length image, and for the photon ring. And then we sum all of them. Okay, well, we extend the domains of these functions, and now we define the total intensity of model 2. It's like Tesla, model 2 and model 3. Okay, and here we just reproduce the same information as before with the list of data, but now, well, we can compute the integral to estimate the contribution of each sector. Now we can see that the directive match represents 90% of the intensity, the length image 9.5%, and the photon ring is 4 times, well, 2.5 times more than in the previous case. Okay. And now we can add the 3 profiles, and this is what we get. And from this curve, we just need to plot it in polar coordinates with the density plot command. Okay. And what we will get is an inner region with some brightness, decay, and then an outer region more brighter, and then a sharp decay in intensity, which is this thing. Let me make it bigger. Yes. Okay. As you can see, this is the same black hole with a different accretion disk, and the optical properties are completely different. But it's the same astrophysical object with a different distribution of matter around it. Okay, so now you can see the importance of understanding the physics of the disks, and in order and see define strategies to extract information about the background from the observables that we see. Okay. As I said before, the outer ring, this one is very bright. This is because the second peak, this peak is higher. Okay. And this region is very bright because it's very broad and sufficiently high. Okay.
How do you do your interpolating functions? So
Yes.
to do the interpolation first order?
First order. Yes, otherwise you can do different interpolations, but I didn't like the outcome. There were artificial effects. If you put second order or another polynomial, then there are effects that I didn't like, so I restricted to the first order interpolation.
The question is how much information do you think would be lost by this approximation?
Well, basically nothing. If you want to improve the approximation, just increase the number of geodesics, because that is the raw material. Okay, if you put like 2,000 geodesics, linear interpolation is more down. Okay, and then we have the Model 3 that we all want in our garage. Okay, and this is an accretion disk that falls down to the black hole. So this is really matter that is being accreted towards the black hole. So it is being absorbed by the black hole. So we use this profile here. Okay, it goes down to R equal to 2, nothing beyond, because we cannot see if there is anything beyond the event horizon. But from here outwards, any photon emitted here will be able to, not any, there are photons from there that will be able to escape. Okay? This is the black sector that we computed at the end with only 20 geodesics. Okay? Because there are, between the photon sphere and the event horizon, we saw that the photons emitted from far away were absorbed. But what you need to think is that there might be matter in that region that emits photons from there, so they can escape.
And that profile is space station. It is the same at any time.
There should be a continuous flow of matter, yes, to keep this safe. Yes. So physically, I don't know how realistic this is, because you need a continuous flow of matter falling into the black hole. But the truth is that we expect that matter is being absorbed by the black hole. Okay, again, the same thing, redshift factor, and then you modulate the information we have about the geometry with the intensity profile. Okay? And then we get these different intensities for the direct image, lensed image, and photon beam. So we see an overlap. We define the interpolating functions. We improve the domain of the interpolating functions. And then we estimate the relative contributions. Now the direct image is 92%, the lens image is 7%, and the line ring is 0.28%. Okay, now we add the three intensities, and this is the intensity profile that we get. Okay, you can see this region, the innermost region, is not the brightest. Right? Remember that the intensity profile was highest in the internal region, but also there the redshift factor is bigger. Okay, because at the horizon, the redshift factor is multiplied by 0. So you don't see anything. The photons are absolutely redshifted. So even if the intensity profile is highest here, due to the strong redshift, that is not the most brilliant or bright region that you observe. Okay? And as you can see, this is quite dark. And the region of the photon ring is the region with the maximum intensity. And it's not too narrow. Okay. And then if you compute, I'm going to compute the intensity profile. First, I will show you the intensity profile, and then I will compute it explicitly just to show you the time it takes. Okay, this is the new intensity profile. Okay, so same geometry, 3 different models. The optical appearance is completely different.
The lens shows the channels like this.
Yes. So let me compute this. So this is 4:15, 40 seconds. Okay. Let's see how much it takes. I think it's like 2 minutes and a half. So basically, this is all I wanted to show you. Okay, this is how we computed the first intensity profiles. And now we are able these are elementary notebooks that focus on the pedagogical part, but you can use them to produce your own images. So, and then you can improve them in different ways, and make things more automatic and other things.
Okay, but the question is if you want to consider other geometries like someone was asking, or you want to change the here probability to something else.
You
It's
just need-
going to be a very difficult exercise.
Well, that depends. If you have spherically symmetric objects, like now this is a Schwarzschild, but you can change it and add another parameter that has the that turns this into a black box. The models of Visser and Simpson. This notebook, you just need to change one number from 0 to non-zero. And if you want to study the resonant nostrum black hole, for instance, with electric charge, you just replace the function A, compute the geodesic equation, the geodesic equation there, and everything else is the same. The objects, this is fully workable. Static objects.
You're right. Yeah.
No, we speak about static, but we have another spherically symmetric that is.
Eloise, no, this notebook is not intended, it cannot be extended to rotating. There was several questions here.
But you have the deal with the one. All black holes are here.
Okay.
Or black holes are here.
Oh, yeah.
Yeah, but here with zero angular velocity is also true. So no, this is done only for spherically symmetric objects. Okay, not rotating. For rotating objects, I have my own ideas, which are not mine. I have read papers, so I wouldn't use this this method. The algorithm is still useful because you know the elements that you need. Okay. But I would use a different code, like there are codes for the computation of geodesics that implement energy conservation with a 3+1 decomposition, and you can put there any metric that you like. So I mean, I would invest my time in those methods. But for the first contact with this topic, I think that the spherically symmetric case and this notebook is sufficient illustrative.
And another 5 years.
And about the location method for the differential equation, I don't really know what to say because I just check that it works with that, and I think I tried to use a different location method, but I wasn't very satisfied with the result with this location method here in the well event to identify the last point. So if you have something to comment on this, please feel free to open your microphone and illustrate us, because I don't know, I'm a user. Yes.
A question about scales. Because of course, the black hole, let's say the horizon and even the theoretical impact parameters. And at the end of, correct me if I'm wrong, at the end of the day, your screen has a length, let's say, which I don't know if it's, let me say, comparable to the, say, 3 kilometers of your black hole horizon.
Yeah, well, basically, the coordinate that you are using in your scheme is the impact parameter.
My ignorance is when you plot the intensity, you plot it against the radial, well, radial, the west-east coordinate. It's right, the vertical. How is that length to see the intensity, let's say, spectrum? When compared with a black hole horizon, you know what I mean? If you plot intensity against y, right? It's against this direction.
Yes.
Is this?
Well, the intensity, I have normalized the intensity to unity.
But my question
For all black holes.
is about that horizontal distance, or how the intensity depends on the distance, where you are, as when compared with the length or the typical scale of the black hole, right? Because my naive question is, well, the telescope is going to have a finite photographic plate, let's say. Right? It's not going to be 3 kilometers. It's going to be like, I mean, I know that the I-COOP telescope is able to maximize the total length, let's say. What I've got in mind.
Yeah, what is the size of the detector? The screen where the photograph can fit, right?
My ignorance comes from when you go to the Ferrari layer, right? They, let me say, they do for an asymptotic observer, of course, but later on what they do as well, is to bring the observer or the source to a finite distance because of the reversal of the light rays.
Well, yeah, exactly. You need these images depend on the location of the observer and on the motion of the observer. So we are assuming that it is static, so there are no additional redshift or blue-shift effects in the motion of the source or of the observer, the inclination of the relative inclinations of the source and of the observer. All these things can be added to complicate things. Also, we are considering that we are very far away from the object. So if the object typically has a size of 2-3 units, we are located at 1,000. So if what we see is really small and will fit in our camera, in our detector. If you were much closer, the black hole could be huge. Okay, then you will need a bigger camera or screen to store all this radiation. But since we are very far away, we don't need anything special because it fits well in our camera.
I guess this is sorted already by the images we see. I mean, in the images we see, we are seeing huge things in a single photo.
Yes, because they are very far away. Exactly. Yes, they are small in the screen because they are very far away. Albert, yes, this method, this notebook can be applied to the spherical symmetric line elements. Just simply change everything that is relevant here for your model is with these functions A and R. I mean, you can even put B if you want. Then you need to compute this function here, okay, which is the right-hand side of the geodesic equation, because this is what you will put here in the geodesic integrator. If you change this and adapt this one-event condition, then you can use any spherically symmetric static black hole, or not necessarily a black hole, or even a wormhole or any other thing that you have. Okay, any other question or comment? If not, I think I will ask you to clap me. Thank you. And then our next speaker is. I forgot because let me take the program. Let me take the program. Yes, yeah. Lesa is at 4. I'm already. I took a lot of the time. So, Leandro, are you around? Yes, Leandro.
Can you hear me?
Yes, we can hear you. Can you just wait, like, I don't know, 5 minutes maybe, because some people left the room for a short break. Okay, so let's wait just 5 minutes.
Right.
Okay. Now, yes.
You can see my presentation.
Yes, we can see. Yes. Clearly. You stole my logo. Okay, I also want to drink something.
I think it's about this.
It's black holes again. Basic things to then
Hey, you need to buy the book next year.
Hopefully it will be next year.
Yeah.
Next year. Yeah. We have to finish all the notebooks.
Yeah.
Everything.
That's really nice.
It's a lot of work.
Yeah, because I don't use that how spherical symmetry. Is that published in there? So this is a spherical symmetry.
But if you have a line element, you guys know. In 2 minutes. Pasa al final. Sí, la suya y o sea, el segundo no inventó la métrica y ya que entonces eso no se encuentra. Sí, por eso básicamente los también puede haber diferentes ángulos. Solamente está inclinado en no puedes inclinarlo así, pero también así. Creo que no tenemos eso es un resultado de hacer fits de la víctima. Sí, eso es de verdad.
When you say that Shannon is doing things, is that, I mean, what you think is done? Yeah, exactly. Using more data, more models, gather these
Okay. So, Leandro,
Hi.
First view was
yes,
straight out
you can
from-
start whenever you want. So, well, let me introduce you. So, our next speaker is Leandro Lessa from the Federal University of Ceará in Brazil. And he's going to tell us about the research.
Mhm. Can I start?
Roberto Maluf, who was formerly here also as a postdoc. And
Well, can I start? But I'm not here.
let's start.
Yeah. Well, hi, good afternoon. Here it's good morning yet. My name is Leandro Lessa. I'm a researcher at the University Federal de Ceará. And today we're talking about my last paper that was published recently. First of all, I would like to thank you to organize, to invite me to this workshop. It's the event is really great. Well, but there's a presentation based in this paper that was published recently. The title of the paper and the presentation are the same. Einstein, Brennan's world and Einstein cubic gravity. Einstein cubic gravity is a type of the high curvature theory. Probably today, this kind of theory is my main line research at the moment. Well, let's start. My presentation, I invited it in 4 points. The first one, I will make some introduction, motivate how or why you need to extend the general relativity shortly, in a specific way when you introduce new invariant in your theory beyond the Einstein-Hilbert term. I will explain a specific kind of this theory called the Einstein gravity. In this case, I will generalize this theory, and then we apply this in a specific scenario and Brennan's world, and then we will conclude it. So how you can go beyond the general relativity, or why you need to do that? Well, everybody knows here that the general relativity is so far the best theory for the gravity. This because we know this is the most perfect match between the theory and experiment. But for another side, we know that has some problems with the theory. Here you can divide this problem into huge categories. One more theoretical that we know. If you try to solve the equation of Einstein, then you know that like some symmetry, like black holes or cosmology, we found some points or regions that we can know well define. So sometimes we call this a singularity. These are huge problems in general relativity. But another problems I think is if you try to lead with the general relativity like a field instead of force, you can sometimes use some tools like quantitative theory, but you know that the general relativity is not renewable. These are another huge problems in general relativity. But for me, this is the worst problems in general relativity. We don't know if the theory, the gravity, have some quantum behavior. You sometimes we try to construct some theory that introduce these new behaviors, but this have a problems. For personally, I think the quantum gravity, the problems with that is just one. We don't have a data. So if we don't have a data, everything that's possible. Just we constructed the theory that introduced the possible quantum behaviors, but like we don't have data, we can't rule out the theory that some theories doesn't represent the reality. So these are a big problem. And another kind of the problem in general relativity is more observational. We know you know that the universe is expanding fast and faster. We don't know why. The equation of motion of Einstein tell nothing about that. If you see the galaxy, we know the galaxies are spinning faster than the general relativity predicted, so you don't know why. In this moment, the cosmology increases. We don't know. You have the Hubble tension. So in this moment, we know that the general relativity is not the end line. So what you do here is propose ways to extend this theory. So you need to finish the Einstein's work. Here I put some possibilities. This theory to modify and extend the general relativity. We know the general relativity is constructed in 4 dimensions. What happens if you add a new dimension? You know, have some theories like Kaluza-Klein theory or Hadron syndrome. You can do another direction if you added a new field like I don't know, Brans-Dicke, scale tensor fields, quintessence. It's possible to modify in this direction. You can make more drastic, hard modification general relativity if you change the geometry. We know that the general relativity is based on Riemannian manifold. Strictly speaking, it's a pseudo-Riemannian, but anyway, but you can change the geometry if you want, like Cartan-Einstein geometry. And another way to modify the general relativity, we can try to lead with this theory with quantum behaviors. We have many possibilities. We have string theories, looking at gravity, etc. But the goal of this presentation is when you want to modify the general relativity, when it add new invariant beyond the Einstein-Hilbert term. So these are the goals of this presentation. So here we will present some property of this kind of theory, higher order theories. You show here some example of that. Here, this presentation is based on just a metric formally. That is, the metric is the only dynamic field. And in general, this model generally exhibit a remarkable property, like is they are potentially renormalizables. It's a good property of that. And sometimes this model can explain the accelerated expansion of the universe. Probably this is the most famous property of this modifications. And in some theory that you can cure the singularity inside the black holes or in cosmology in the beginning of the time, and some kind of this higher order theory. Here shows some possibility of this theory like a Lovelock gravity. This is very famous because the theory introduced a new invariant on the Einstein-Hilbert and a new dimension as well. But probably this is the most famous one is FDR and T is very famous, but you can construct a new invariant instead of the heat shear scale. You can construct this with invariant with curvature tensor or a heat tensor. It's possible to as well. But here is the main high order theory that we will talk today. It's called the Einstein-Cube gravity. I will show some property of that, and then we will generalize this the theory. However, like many modified gravity models, this model can have a serious assumed. Probably the most ones, the worst is the theory, sometime introduction instabilities is problem because this kind of problem is a problem of unitarity. Is a very problem. Is very difficult to lead with that. And another kind of problems is a pathological grid of freedom. That's another huge problem in this kind of modified gravity. Generally, these problems arise to the high derivative introduced by these new fields. So what we do here is try to avoid these problems with if you can avoid the introduction of the high derivative and equation of motion. So this paper and there's a presentation based in three papers. This first is probably the most famous is by David Lovelock that introduced shear gravity, Lovelock gravity. This theory is the most general metric theory in D dimension. at all order of the curvature is important because it's not just a quadratic cube, but all order curvature with a second order equation of motion for any space-time. So if you assume any space-time, like I don't know, black holes, cosmology, Brownian wall, you always obtain the equation of motion until second order. So this is a very good property of this gravity. But this kind of modified gravity is quite restrictive, because if you assume just quadratic term, called a Gauss-Bonnet term, you know it's necessary to work in a dimension bigger 4, because if you, for example, assume 4 dimension, we know Gauss-Bonnet term is just topological, so it doesn't contribute an equation of motion. But these 2 papers that put here is famous as well, that try to avoid this restriction. Here you can introduce the famous quasi-topological gravity, in this case a generalized, and this the main paper that is based this representation that introduced the Einstein-COOP gravity. They lead the second order equation of motion for cubic curvature term, assume space-time with static and spherical symmetry. Here is specific. You need to assume this kind of symmetry, like black hole. For another space-time, a high order derivative appear in equation of motion. So what you try here is generalize this theory for another space-times. So there are many high curvature theory that attempt to introduce the effect of the new invariant without necessarily introduce a high order derivative in equation of motion. So what you propose here is generalize the Einstein-COOP gravity to warped space-time. Well, what we do here is construction in Einstein-COOP gravity and a 5-dimensional curved space-time as effective field theory. This point is important because this approach that you use here is like effective field theory, because if you assume that, you can avoid some problems common in this kind of high curvature theory, like unitary problems and pathological degree of freedom. Besides the usual Einstein-Hilbert term, you consider quadratic and cubic term as a perturbative correction of the Einstein-Hilbert term. Here, of course, the quadratic term cannot be ruled out because here we have 5 dimensions, so this term is important here. So the first term we will have in this action, we have the Einstein-Hilbert plus the quadratic interaction, and the last we have the cubic interaction and plus the matter Lagrangian. In the quadratic interaction, you have the total of 3 possibilities of invariant given by this expression, and the cubic one we have the total of 8 possibilities. In the scenario, more general cubic term P is expressed by this equation. We have the 8 possibilities, so 8 parameters, 8 cubic couplings. Unlike Lovelock theory, which excludes contribution from the space-time with a dimension is more 6, the cubic interaction that mentioned a term contribution of the equation of motion in 5 dimensions. But how? Here you consider some conditions. Based in the paper that introduced Einstein-COOP gravity with the invariant P, you can show that if you follow a parameter choice, this given by this beta 7 and beta 8, it's obtained when we assume your theory share the spectrum with general relativity. If you assume that, we will obtain these 2 conditions. If you replace this condition and this general Lagrangian, you can obtain the famous Gauss-Bonnet term in quadratic interaction, but it's not enough to determine completely the cubic interaction. We need to put in new conditions. So what you hear is study this theory in a specific scenario. We consider here the Brownian world. Here we consider the standard model like Henderson drew, given by this flash 3 Brownian warped metric. this equation. However, with this privileged two parameters choice, beta 6, or beta 8 and beta 7, the equation of motion for this choice until is even higher than second order equation in a cube interaction. So ultimately eliminated this, we once again explore the freedom of the parameters. Here you use some mathematical softwares to obtain that, but if you choose just another condition given by this expression, here is in the beta 6, you finally obtain the equation of motion without a high derivative contribution in the equation of motion. Indeed, you have here the equation of motion. This equation is equation of motion in Einstein. Here, this term is a contribution of a Gauss-Bonnet term, so the quadratic term, and here is exactly contribution of the cubic term. Indeed, we have any high derivative theory introduction by mean the high curvature theory. What you do here now is try to solve this equation in some scenarios. So here I think three brand. Once we obtain the modified gravitational equation to the warp the Einstein cube gravity, let's now consider correction to the quadratic and cube modification on thin brand. Here's again the standard Henderson models. Here don't consider the scale effect. And you have this ansatz for warped factor. If you replace this inside this modified equation of motion, you obtain this cosmology constant given by this. In order to have the 5 answer the C, the book solution, that is, you can find some upper bound for the cube, so for the cubic coupling given by this expression. So then the strength of the cubic term lambda beta increase as the book curvature given by this expression increase. So this equation provides us an upper bound for the cubic coupling stream from the external dimension. So now you can consider this effect of the scale field. So what we do here is study the think tree brand now. In this case, we are split into different regions. The first one outside the brand core, we expect the field the heated vacuum volume. So the relative of the scale and the potential the scale field as well it's 0 in this region. If you assume that and replace this modified equation of motion, we will obtain again another upper bound for the coupling, the cubic coupling. Here, just a choice, but we don't consider it as a factor of the Gauss-Bonnet term. And another region is here in the bronze core. Here you need to use the well-known BPS formalism. Here we'll have this. Everybody work with brand will know that it's like a cake receipt. You just assume that. We assume that the derivative of the warped factor is in relation to this function called the superpotential. If we replace that in the modified equation of motion, you obtain these two equations. Now what you do, it's common, you assume the phase, the ansatz for the superpotential. Here you choose the Sine-Gordon model. If you replace this function inside these two equations, you can construct some graphics. We have, for example, here the potential and functions as scale field. Here the energy density, warped function, and the scale field. You can see here this is more derivation in relation to the general relativity, but it's obvious because this is more derivation are expected since we assume that a small value of the cubic coupling for the effective field approach to be valid. So, and then we'll discuss some things about the gravitational fluctuations. Here we study the behavior of a Brownian solution and the perturbative level. So you study the propagation of the small perturbation up the curvature modified gravity Brownian found prevalent. So let's now consider the tensor function up to Brownsville solution of this form. Here is an important point because in the paper that show us the Einstein cryptogravity, the author assumed that the gravitational function lives in maximum symmetry background. Here we generalize this idea because we consider now a non-maximum symmetry background given by this expression. So from here, you analyze the fluctuation on a cubic interaction only because the Gauss-Bonnet theorem has already been done in this paper and recently published. So what you do here is just analyze the contribution of the cubic interaction. After the many exhaustive calculation, here you use again the mathematical softwares. We thought it's necessary to impose additional condition on beta, the parent of the cubic interaction, to eliminate the high order derivative in equation of motion. Equation of motion, of course, now on the gravitational fluctuation. So you're necessary to put another conditions. Again, if you assume there's another two condition here, now it's in beta 4 and the beta 5, you can eliminate it, the higher order derivative in equation of motion. Indeed, we have here the equation that describes the gravitational fluctuations. Indeed, we have any high derivative contributions. So you can make something with this equation, but here I will show just stability assumed. What you do here is perform the usually Kaluza-Klein decomposition given by this expression. We replace that in this equation, you obtain this two equation. Here again, if you work in a Browns word, you know that it's like a cake recipe. We just make some transformation of coordinated in this equation and use some analogous supersymmetry quantum mechanics approach. You can write this equation inside that and use some result of SuperSUSY. The SuperSUSY like symmetry guarantee in this case the stability, the analysis of the Kaluza-Klein mode is because there is not any tachyonic Kaluza-Klein gravitational modes. What you do here is we are presentation what you investigate the effect of a high curvature term of the cubic ordinate within a Brownswood mode. We propose a cubic effective gravity theory inspired by the Einstein cubic gravity, characterized by the invariant P determined for 80 parameters, 80 betas. So you had to fix the 3 of them. The first two, you ensure the spectrum is shared with a general relativity, and you choose another one. So if I sum that, we obtain the second order equation of motion for the warp factor of the cubic ordinate curvature. So it demonstrated that theories give rise to thin brands solution, -200 type. We introduced the first odd BPS formula to derive thanks brand solutions. Next, you derivation equation govern the tensor gravitational fluctuation explicitly. You need to fix another two cubic parameters, beta 4 and beta 5, and then we obtain the equation of motion. The equation obtain the second order equation of motion for the gravitational fluctuations, and finally demonstrated this model is stable. This implies the absence of tachyonic Kaluza-Klein modes within approach framework. So it is. I can hear.
So, any questions in the room or comments?
Any reason why you introduced 2 modifications to the GR action? One, you changed the dimensions to 5, and
yes,
you introduced a cubic Einstein cubic gravity. Why the 2 together?
Sorry, I can heard the end. Because you're not near the microphone, so it's not good.
Right, so my question is why you introduce two modifications to your graph here? Einstein cubic plus 5-dimensional space-time.
Yes. In this case, we assume the space-time with 5 dimension. So you need to because when you assume that, you need to introduce beyond the cubic interaction, the quadratic interaction, because it's important 5 dimension. So if you assume that in this theory, you assume the different scenario like a Brownian's world. So if you assume that in this specific Einstein gravity, you show that you can show that this theory introduce high derivative theory in this case. So you need to modify this theory for obtain the equation of motion until second order equation.
I guess also because they use Gauss here. So this is the fifth in moves and
More than 4. All right.
Okay, so there is another question in the chat. So Andrei Petrov is asking that what happens if you restrict the cubic terms to just the scalar curvature, the mixed scalar cubic, if the behavior of your system would be different.
Right, and the stats, right?
Mm-hmm.
Can I can see the charts here?
Where there is next to the participants.
Yes.
Now we are seeing your not that chat, that's your WhatsApp.
Right, he said if you consider the only sum of cubic terms, said cubic of scale scale curvature will behave very different. I think it's yes, because in my approach, I assume all possibilities. If you assume, for example, just the heat scale cubic, it's a possibility, but in this analysis, I consider all that. But I think if you assume just one, for example, it's very difficult to eliminate the high derivative theory or high derivative in the equation of motion. Like a Starobinsky model, we have just one contribution with a quadratic term. The consequence of that is to introduce a high derivative in the equation of motion. But you can play with another configurations.
Okay, any other questions or comments? If not, then let's thank Leandro again.
Thank you.
Okay, you can stop sharing your screen.
Yes.
Have last speaker today. Okay, the youngest member of our group. His first talk for us. So do you need a USB?
I have a USB. I think the laptop has no battery, so.
Okay, so but do you have?
Also, I sent my files by email.
Yeah, I have 200 emails waiting to be answered. So but you can use my iPad. Let me see. Yeah. One. Si le trabajamos, pues pasa las slides. Sí, sí, pasa. Okay. La función es así. pero se orientan hacia la siguiente semana. Perfecto. Vale, entonces, vale. Sí, Okay, so our next speaker is Javier Marañón González. He's a PhD student in our group and here in Valencia, and he's going to tell us about adiabatic regularization for spin buckets.
Thank you for the introduction and welcome to everybody, Valencia. And my talk is about adiabatic regularization, which is a special kind of with the extra term. And the box operator is just the generalization to curved spacetime of the wave operator. Okay, how do we make the theory quantum? We just expand the field in modes and create annihilation operators and define a vacuum state. And you can find a really nice introduction to the topic and adiabatic regularization in the famous book by Parker and Thomas. So especially all this first part about the scalar field and quantum theory of the spacetimes in general. Okay, so what I was talking about the vacuum. What kind of condition can we use to specify physical vacuum states only? The condition that uses the adiabatic method is called the adiabatic condition, and what basically means is that you take that the energy of a particle of a given momentum k, if that energy is way bigger than the energy scale of the space-time, then this particle mode is not produced. So the particle number is approximately constant in that mode. And that condition can be expressed as an asymptotic expansion in terms of adiabatic order, which I will explain later what exactly means. But basically, you expand the modes of the scalar field in this way. This is just convenient for normalization. And you have a mode function H. And it is H when you expand asymptotically in terms of this W. This is called the WKB answer. And W at leading order is just omega, this omega. And then you have greater adiabatic order constituents. Okay. Fine. Okay. So the answer that I introduced ensures proper normalization of the nodes, but I will explain more on this in the second part because it's actually a very subtle process in that case. But here with that expression, we have the field equation reduced to a harmonic oscillator equation for the H with a time-dependent frequency. And once we substitute the asymptotic expansion for H, we have this equation of motion for the W. And now I can explain what I meant previously by adiabatic order. If your spacetime, your cosmological spacetime is slowly evolving, its time or special derivative will be smaller than the previous one. So in that sense, you have that at the leading order, you can neglect the time derivatives. This sigma, as it has second order time derivatives, is of adiabatic order too, so you can also neglect that. And W at first order is just omega. And then you can, now it worked. If you actually do this recursively, you have that the first, well, all adiabatic orders are vanishing. And for example, the second adiabatic order is just obtained by plugging this with omega and kind of solving this side for omega second adiabatic order. And you can repeat this process as much as you like. Okay. So the thing is that this expansion essentially encapsulates the ultraviolet behavior of the nodes, of the modes. So it's very good to isolate the divergences and remove them. Also, the mass is very important in the adiabatic method because it ensures that the whole asymptotic expansion is also non-divergent in the infrared limit. For example, if you try to calculate this quantity that appears in, for example, when you try to compute the energy momentum tensor and all of that, which is just the subpoint function in the constant limit, you have this formal expression that is divergent. If you plug in the asymptotic expansion, you see those divergences explicitly. This is the one that appears in flat spacetime that can be solved by normal ordering and all of that. But here we have another more divergent quantity that appears due to gravitational interaction. And all the rest terms are finite. So for this case, only the two first adiabatic orders are sufficient. And okay, so how do we regularize? Which I denote with this during the whole of the presentation. You just take the mode contribution and subtract all the terms that are divergent at the whole adiabatic order, because sometimes there will be finite contributions there that you also need to subtract from consistency. Okay, so now a brief introduction about the trace anomaly. If you compute the trace of the energy momentum tensor for the scalar field, you have this expression. It is for an arbitrary non-Millipant coupling type. And if you notice, for chi equals 1/6, the first two terms vanish, and you only have the last term. But if the mass is 0, there is no trace. And that essentially is very well connected with the conformal symmetry, which is this, but I won't delve too much into this. So essentially, the thing is that if you have a classical field with these values, you have no trace. But once you quantize the theory, you see that due to gravitational physics, this trace is non-vanishing. This is also known as a trace anomaly. So, okay. How does this arise in the adiabatic method? So you just have this term here for the conformal field, and you notice that I included the quantity that I was talking about previously, that includes the first two adiabatic orders, but I also have a fourth one, which is finite. So why is it here? Because when you normalize the whole energy momentum, it diverges up to fourth adiabatic order, so you need to include this fourth term. But once you take the trace, that quantity is no longer divergent, but it gives a finite contribution to the trace. So all of this is just this, because this one doesn't contribute once you calculate. And once you put the expression for that, you get this, which is a completely covariant expression. So this is how you can get this kind of results with the adiabatic. But what happens when chi is not 1/6? Then the thing is that the whole, the first two terms that I was talking about no longer vanish, so they will also give a contribution. Also, the whole trace is divergent up to fourth adiabatic order, so one order bigger than the other case, but you can still get an extra contribution due to this quantum effect, and this is what is called the anomalous contribution, which is just this term. So it's produced by the same mechanism as before. So the only thing is that this quantity is independent of the mass really, so the massless limit doesn't affect it. So that's why you get it. So you have a very similar expression. So that is what you do with adiabatic method for scalar field. And you can do this because there is no problem once you take the massless limit. You need it to properly use the method, but at the end you can take the limit, and the numbers of degrees of freedom are just 1 and 1, so no problems. But for vector fields, we have a problem, because if we take mass non-zero, the most natural candidate is the Broca theory, but then you have 2 transverse degrees of freedoms and 1 longitudinal, and you have an extra constraint. But for Maxwell theory, which takes mass identical to 0, you only have 2 degrees of freedom, which are physical, and the other is just gates constraints. So it's not very clear how you do the massless limit if you want to have a properly regularization scheme using the adiabatic. So for that, you have 2 approaches essentially. What people initially tried is to use what I'm going to describe here, but then they found that the fourth adiabatic order is divergent, and they didn't know how to continue, because that doesn't happen for the conformal scalar field. But as we see, it happened for general scalar field, so it's no problem. And then what they did is just they used a different approach. Instead of taking a physical mass, they assume gates invariant to hold, and introduced for that a Struckelberg-like field. And at the end, well, they also needed ghost fields to remove all the gates non-physical degrees of freedom. And then the massless limit can be taken, but the whole process is very involved and it's not simple at all. So we thought maybe we could use the original approach and see if we can make any progress. It's just take a physical Broca field, deal with the longitudinal polarization, and see what happens in the massless limit. Okay, so that leads us to the second part of the talk. And just as before, we need an action. This is the straightforward generalization. Here, there are no extra non-minimal terms. These are the field equations. And now you can also take a covariant derivative of this whole thing. The covariant derivatives don't commute, but you can use properties of the commutator and the Riemann tensor, all of that, to get this equation. So if the mass is non-vanishing, you will have this exactly. And it's not a gauge choice in this approach because there is no gauge symmetry. It's kind of one of the advantages. Okay, so how do we deal with these 3 polarizations? It's really basic. We need 1 polarization vector for each polarization. This is how it looks like in Minkowski space, where you just essentially need 2 orthonormal 3 vectors that are also perpendicular to the direction in which the wave is propagating. And those ones are called the transverse polarizations for that. And then you introduce this funny vector, which is just longitudinal to the direction, so in the same direction as the wave is propagating. And all of this is properly orthonormalized. Okay, but once you go to a cosmological homogeneous space-time, then you need some changes. which I outline in red. First of all, the frequency is time dependent because of the scale factor, but also you need to introduce another function which is unknown in theory, which is not the same W as for the scalar field, just they happen to share a name. And in the flat spacetime limit, this will coincide with omega, and we will recover the previous polarization vectors, but here, in general, they don't. So we have to deal with that. Okay, so we express the two polarization vectors, the two polarization modes in this way. This will be clear shortly, and we have now one H function for the transverse modes and one L function for the longitudinal ones, for the only longitudinal ones. Okay. So how do we normalize the modes? Normalization is important because we need proper commutation relations among the quantum operators. One way of doing that is introducing this inner product, which is just evaluated on a surface of constant time. And if we are able to normalize the mode such that this condition holds, then there will be usual commutation relations and it is sufficient. For the transverse modes, this just simplifies to that. This is the same as the scalar field, so nothing new here. And for the longitudinal one, we have a more involved expression which is just kind of a constraint in the W, which we need to take into consideration. Okay, now what happens with the field equations? The time equation is just trivial for the transverse modes, which essentially means that it's zero by construction. And for the longitudinal, it gives an expression for W in terms of these functions and the scale factor. Now, from the spatial equations, we get all the dynamics of the systems, how these H and L evolve with time and what happens. And this constraint is just dependent on the other two, so nothing really happens, but it's just trivial for the transverse modes and is satisfied on cell for the longitudinal degree. So for the transverse one, we have this equation of motion, which is just the way a scalar field of chi equals 1/6 will behave. So we are expecting, at least classically, that these two transverse polarizations behave as two conformal scalar fields. And for the longitudinal one, we get a more involved equation, but if you take the massless limit, it behaves as a minimally coupled scalar field. So we are having this in mind and see if we are able to replicate, or better said, to keep this behavior in the quantum region. And as a funny comment, this equation is also a chi equals 1/6 if we take the very massive limit, but that isn't really a conformal field because you will have here only M and not the K parts. It may be useful for some other context. Okay, so for quantizing, we need to introduce this ansatz here that allows us to give this W function. And now we are able to use the adiabatic. All of the above that I have described just gives proper normalization of the modes as well and is consistent with the field equation. So everything is working as intended. And now the equations of motion just reduced to this form for the H and L functions. So that's why we can apply the adiabatic method. They have different values of sigma, but the whole process that we explained for the scalar field just can be done again. So, but now we have these two functions for the transverse and longitudinal degrees of freedom. Okay, once we study why we study the trace anomaly, it's because if your method is able to reproduce the trace anomaly, is that you're doing things consistently, right? So this is the trace anomaly for the program. Now we expand the operator into modes and get this formal expression, where this is the contribution from the transverse modes and this is the contribution for the longitudinals. As we see, it's more involved than longitudinal ones. So it will be more. The transverse fourth adiabatic order is finite, as happened for the conformal scalar field, so that's okay. But if we study how does this fourth adiabatic order behave in the ultraviolet, we see a box of R divergence, which was also present in the case of a minimally coupled scalar field, but people weren't expecting that for the Broca field, and that's why they stopped here. If you have a spacetime in which this is zero, like for example the zeta, this is completely divergent. So,
Sorry, the angular bracket,
yeah.
the averaging operator.
Oh, you are calculating this as the expected value of the trace using vacuum as a quantum state.
So I need to also take the expectation value metric, the previous slide.
Okay. Yeah, because in this approach we are considering that general relativity is a fully classical theory, and we are only putting quantum fields in a curved spacetime and seeing what kind of new physics that gives. It's an intermediate approach between a fully classical theory and just purely quantum gravity theory that we expect to hold in some regime. Okay. So this is how the thing looks like for the scalar field and for the longitudinal polarization. We see that there are some finite terms that will give rise in that context to the anomalous trace, and here to the analogous of that. And the divergent parts are very, very similar, which suggests that these two fields behave very similarly, but not identical. Okay, but these expressions are not covariant, and we are not able to make them look in a covariant way. They are local, but not covariant. So what can we do from that? And what we discovered is that if you subtract only the finite terms, this one in the massless limit, because this one is not covariant, can be expressed in a covariant. So if we now turn to the renormalized trace and subtract the first fourth adiabatic terms, which are the ones that contain all the divergences, we have this relation. But this is also in the massless limit, and we are assuming that there is no finite contribution from the modes. This is what happens for the conformal scalar field, where the modes are only a divergent term that you subtract with the adiabatic regularization and introduce finite quantities. But we also studied the Broca vector field in the sitter completely to see if there are contributions from the modes, and we couldn't find any. So we suppose that this holds in general. So the transverse degrees of freedom behave as two conformal scalars, and once we put everything together, we get this expression for the trace. But this part is exactly the trace anomaly of the Maxwell field. So, well, not only exactly, but also this term, the box of R, which is a term known to be dependent on which regularization scheme you use. So we agreed with this term in the other approach that I mentioned, and also in other approaches like zeta function regularization and point splitting, which, for example, for the case of point splitting is equivalent to adiabatic regularization, but adiabatic regularization can only be performed in homogeneous universes yet. So we can generalize all of that to the whole energy momentum tension, which I will discuss briefly. But that essentially means that we have the adiabatic regularization approach working for spin zero fields, spin 1/2 fields that was also done here in the group by these people, and then continued by several others, like for example, Adrian Del Rio is also in the group. And now we have a construction that is simple and efficient for spin 1. We're starting to look at spin 2, but we are having some difficulties because if you add a physical mass, then the graviton just has 3 extra polarizations. You have to deal with ghosts and potentially with non-trivial interaction with the fields that generate the geometry itself. So we're starting to look at it, but it seems a bit daunting. And this is the main result of this. But some very interesting comments that I would like to remark is that if you just focus on the transverse polarizations of the Broca field, these are not Maxwell theory. And if you just focus on the longitudinal, this is not the scalar field, which is the behavior that we were expecting classically from the equations of motion. What that means is that if we really want to replicate the quantum behavior of a massive or massless vector field, we need to use that theory. Because sometimes you see people use, for example, instead of studying Maxwell theory, they just study a conformal scalar field and try to mimic the behavior, but that doesn't contain all the physics. So that's an interesting comment. And this is the final relation between these two fields. And yeah, so these are the references that I used. And thank you very much for your time.
Okay, we have time for questions and comments.
Yes, please.
I don't know, do you know what scalar field is?
A little bit, but I didn't know.
Have you tried to apply non-regularization methods for Maxwell and scalar field? So, a consistent way of taking this n to zero limit while preserving the number of bits free is to introduce scalar fields
Yes.
together with the protraction, and then taking the n to zero. And the Stuttgart couple in a way in which you get 3 degrees of freedom at the end of zero limit. The scalar one is the longitudinal mode, and the other two are and they are enough. So, have you tried to implement the dialectic regularization using this kind of technique?
So instead of, okay, what is done in the literature is more or less what you are describing, but instead of the Broca theory with pure Maxwell theory. So they need to also introduce ghosts to remove the gates, what gates is actually doing. So are you suggesting something intermediate? Like
Also, so what they did in that paper is to
actually, yeah, this was the original one, but then people also did it here.
So they was to find a dialectic regularization
For vector
fields
fields,
from the scalar or something like that.
No, they just wanted it for the Maxwell theory, only for.
But why would they use Stuttgart for Maxwell? That's why
Because they need to keep the gates invariant.
because they want to do it in an arbitrary gate.
Yeah, and what they happen is that if you keep these gates invariants, then the box of R term is different. And for one particular choice, they agree with a result and set a function regularization and all of that. But yeah, the problem with that approach is that you need to also introduce the Stuckelberg field and 2 additional ghost fields. And you need to find adiabatic expansions to all of that.
Why the ghost fields?
Because you need some way to remove, for example, your vector field has 4 components. So they need to introduce 2 to get rid of 2 non-physical polarizations. In our approach, this is not necessary because we have this constraint of nabla mu a mu, which removes one of them and only 3 remains. So that's why they needed the ghost.
I think, I mean, you should be able to do the same with Maxwell. I don't know.
But using only Maxwell theory or Broca theory.
Broca plus Maxwell has 4 degrees of freedom, and then you take the counting limit, and you end up with a 3 degree of freedom theory.
Yeah, that maybe no. I mean that, as far as I know, it's not done yet. But the only problem with that is that you will only be describing Maxwell theory, for example. But you will probably reproduce Maxwell theory like more directly. You will get straight away the trace anomaly.
Oh, yeah, you're right. I think in program
Yeah, because in the absence of gravity, once you take the massless limit, this longitudinal polarization decouples from everything. But in a quarter space-time, it couples to gravity, so it still is doing fine. So, thank you.
Okay. Any other questions or comments? If not, let's try again. And this is the end of today's session. So tomorrow more, same time, same place. Okay. Thanks for coming. Thank you everyone online for staying there and for the questions and what to say. Lo hemos causado ya, porque ya no veo. Lo hemos usado. Ah, sí. Bueno, sí, yo cuando terminé la mañana, me daba de tiempo. Me rápido, que es material. Gracias.